This is a little preview demo of a mapping software written by Frank Swin at Middlebury College for educators and students to help visualize various concepts, mainly with multivariable calculus, the meaning of the derivative, continuity, Frenet frame, all sorts of things we'll see in a moment. The interface is pretty simple. We've got choice of coordinate systems, Cartesian, cylindrical, polar, or spherical. It's about showing mappings. You can just have it plot a surface if you'd like without the domain, or not show the image. So you can toggle the domain or the image of that mapping on or off either at startup or during the display. So the interface is pretty simple. You just define your variables. X goes from 0 to 10. That'll be a free variable. Y 0 to 10, say. The variables can depend on previous free variables, of course, as usual. Or they can just go from constants to constants. The bound variables, say sine of x times cosine of y to make something pretty. Go. And what we'll see is the domain over here on the left, the image over here on the right, and it's, the surfaces tend to be the nicest to look at because they're two-dimensional. So that's what we're going to start with. The controls available, you can toggle on and off the axes if you want. You can show just the domain or just the image. You can not show the controls if you like and get a full screen display of something. For now, we'll just do everything. So everything and the controls. Various things you can do to show extra features of your shape. Again, this is from the XY plane to the XYZ space. Each Z is being assigned sine of x times cosine of y. I've kept coordinates off of this. There's not a lot of numbers floating around because it muddies things up. Maybe there will be a flag in a future version to show all sorts of coordinate numbers and everything else, but to get the concepts across, I think the coordinates may be more than you necessarily want, the actual values. So first thing you can do is show a point. You can navigate that point around, and you notice on the surface it's set to have a little cone of visibility. So if it's obscured by the surface or region, you'll actually see through the surface a bit to get to it, just to get a sense for what the mapping does. Each x and y in the domain maps to a point in the codomain. That's the definition of a function. So other things you can do, you can zoom in and out. I can zoom in on that point. You can see the function looking a bit more linear, I guess, affine at that point. The further you zoom in, of course, the more linear it looks, and we'll talk more about that later. We can demonstrate the meaning of the derivative pretty well this way. We can also zoom out a bit. Zoom out a bit. We can also ink up the surface. Either put a grid on it. Even if you're not zoomed in, you can put a grid on it. Maybe that helps you see it. You can alternatively put a fixed scalar field, which is just giving red, green, and blue according to how much x, y, and z are in the coordinates. Also, this field is pulled back to the domain. So the field is put on the image. The pullback of that field is on the domain. So if you choose to talk about parameterization and pullback in your course, well, it's a good place to see it right here. Again, the scalar field, so to speak, value at each point in the codomain is pulled back to the corresponding value on the domain, transforming a field on a surface to a field on this two-dimensional region. You can mix the grid and the scalar field if you like, obviously. So getting rid of the ink. Other things you can do, neighborhoods. Maybe you want to talk about continuity. Well, as usual, you see points mapping to points, and the points gotten very, very small just to not distract from the view here. Again, this may be a bit sluggish because it's trying to record the screen and do some OpenGL. You can show the delta neighborhood of the domain point if you choose, and resize it as you see fit up to a reasonable size. It's exponential scale here, so you'll get it up to a fairly big size and down to as small as you could possibly want. Smaller than you'll be able to see, probably. You can also show the image of that. If you want to talk about mapping sets, well, there's an open ball around the point in the neighborhood, and there's the image under the mapping. So talk about functions and images that way a bit. On the flip side, you can draw a neighborhood. Let's clear this down to 0. You can draw a neighborhood around the codomain point, the image point here, and that will paint the points in some epsilon ball of color. And you can see that set's pre-image. Of course, there's a bit of distortion depending on where you are on the surface. If you let's make this a bit smaller. If you move it around, you can see, it distort a bit. You can even use this to get all the way down to the epsilon delta definition of continuity if you so choose. Paint a epsilon neighborhood around your point in the codomain. The question is, does there exist a delta neighborhood that maps entirely inside it? And in this case, yes. As epsilon gets smaller, it looks like we're good. Let's zoom in a bit. Yes, as epsilon gets a bit smaller still. Oh, sorry, I didn't do that quite right. Yes. So you can play on and off with neighborhoods. You can also talk about preimage of open sets being open. Here's a epsilon neighborhood in the codomain and its preimage. Well, you can see that around the central point you can get a delta ball to fit inside. So both the forward moving and the backward moving direction of continuity moving into the topological definition both can be illustrated this way. Let's clean this up a little bit, zoom out, get this, go back to normal coloring once you get rid of neighborhoods. Other things you can do, you want to talk about the meaning of the derivative? Well, fantastic. The derivative gives the best linear approximation to your function. So if we show vector here, we can show a vector in the domain and where that pushes forward to in the codomain. That's the linear transformation that the derivative is. If you want to see the meaning of the derivative a bit better, perhaps you show the displaced point. So here's a point, central point. That's what's moved over here. You've chosen a vector. Well, that's the displaced point in the domain. That's an exact displacement. A central point plus a vector gives another point. Of course, once you map forward, the point maps as the mapping says, and the vector maps as the derivative says, and they're not exact. Again, the derivative is the best local approximation. The smaller the vector is, the better the approximation is. Move away, it's worse. Another good place to use zooming here, you can see, let me rotate this around a bit, you can see the function looking more and more like a linear transformation as you zoom in. So here, once I've zoomed into 1/2 unit by 1/2 unit in the domain, you see it's a bit off. Maybe I should flip it around so you can see a bit better. You see it's a bit off, but it's pretty close. As I zoom in even further, maybe, an 1/8, now it's nearly dead on, right? My linear approximation is very, very, very good. The farther you zoom, the better the approximation is. It's the meaning of differentiable function. Other things you can do, let's zoom back out here. If my machine doesn't die during this video. Okay, get this all cleaned up. Whoa, get this all cleaned up here. So get a good view of everything. Let's get rid of the vector. Oh, and the displaced point. The vector and the displaced point. You can also see some geometry. There's not much geometry built in yet. Right now you can see a frame. In the domain you see a unit vector in the domain and codomain. Well, unit according to how you're viewing. And over in the domain, unit vectors in each direction, x and y, and where they're pushed forward to. The images under the derivative are the corresponding pink and green vectors. And for a surface, you'll also see the normal. I probably will make that a separate checkbox in the future because it belongs somewhere else. And as you move the point around, you see both the derivative and the normal vector changing. So, it's a bit of eye candy, but I think it's all meaningful eye candy for the students. The last thing you might want to do if you want to talk about level sets, so I don't really approve of that term very much, but whoops, you could do it if you wanted to. Then the z-field is a way to do that. So let's get rid of geometry. Z-field. You can put a height field, so to speak, onto the whether it's a parametric surface or just a graph of a function like this, and you can put a height field on it. And of course, the pullback of that height field's on the left. So the height field's on the image. The pullback of the height field's on the left. I can get rid of the point, I suppose. You can choose to show the gradient field if you like. You can talk about rates of increase and decrease, and speed of increase and decrease. You can also cut off your surface to really see the, so to speak, level sets. You can cut off your surface at various z values, and of course where the surface stops is the over here on the left. This boundary here is the level set for a given height. I suppose you could use to talk about Morse functions and all sorts of other things as well, but just things to think about. So again, there's a bit of eye candy involved, yes, but the idea is to pull your students into the concepts a bit better and let them see stuff better than you can draw it on a chalkboard. And I think in a way that's intended to be seen, as opposed to, say, Mathematica, where there's just a canned product that does everything. This is really for viewing mappings and shapes. Just to clear this off, let's show something a bit different before we close off the video. You can do a different surface. You can do spherical. So theta goes from 0 to 6 pi. Phi goes from, pi over 4 to pi over 3 times pi over 4. And rho is going to be theta over 6. I don't know. Just to do something pretty. You can do all kinds of parametric surfaces this way. Again, you could choose to show just the surface, or maybe even without the axes and just talk about shapes. But putting everything back up again, you can see the rectangle in the theta phi plane mapping to this spot. All the same stuff works for the parametric surfaces. You can do neighborhoods. You can, put a grid on it, which is pretty. You can put ink on it, which is also pretty. See a pullback again. Geometry Z field. You can cut through the surface if you like. You see the mapping there. Just get a sense for what's going on. So again, that's the objective here. What else do we have? Well, you can of course do smaller or higher dimensional things. Suppose you're wanting to do a surface integral or an integral in calculus. Well, you want to parameterize a part of a ball. So you have theta go from 0 to pi and phi go from 0 to pi over 2. It's on the top half, and rho goes from 1 to 1.5. And you can view a region as well. Again, here's the region as it sits in rho theta phi space. And here's what it really, so to speak, looks like in XYZ space. And implicitly, there's a mapping there. So that's why it's still looked at as in the same way. You can do a lot of the same stuff with it. On the lower dimensional side, you can just do a curve. Have just one free variable, and you've got a curve. There's not as much to see with the curves. That's rather uninteresting one, I guess, a semicircle. But you can do some extra things with them. You can still show a point and vector and zoom in. Geometry, you have an option to show the frame. Tangent, normal, binormal, they're color-coded here. Tangent, normal, binormal, red, green, blue. For the curve, as you move the point around, you see tangent, normal, binormal change. You can choose to scale that frame by the magnitude of the speed, curvature, and torsion, if you like. And you see it this way. Of course, the binormal's gone away because this is a planar curve. But if it was something different, let's come back to something a little different, Cartesian. For our last example, we could do this for, maybe there should be a clear button. X goes from 0 to 10. Y is sine of x. Right? That's perfectly fine. You don't have to do a z. Z is going to be 0 in Cartesian otherwise. There's your mapping. You can again do geometry. The frame is a bit funky because, of course, at the points of inflection, the normal doesn't actually, it's not well defined. And the binormal, you're going to see alternately pointing in and out of the plane as we change direction of curvature. It's a little bit more sensible to scale the frame, I suppose. There you see the, again, the tangent scaled by the speed, the normal scaled by the curvature, and the binormal is scaled by the torsion, which in this case, again, is 0. And you see it kind of move in and out. So, moving into the lower dimensional differential geometry, you can play with that some as well. Anyway, that's the finish here. This will eventually be available on mathanimations.net. That's mathanimations.net. It will be free, both for Mac and PC. I will certainly take donations to help support the work going on this, and by all means, suggestions. It's Frank Swenton at Middlebury College. That's fswenton@middlebury.edu.